In this lecture, we're going to use logarithms to solve some exponential equations that otherwise would have stumped us. In previous sections, we would have struggled with these. Now we're going to use the properties of logarithms to help us solve this. And as a tangent to that discussion, we're also going to talk about the change of base formula. Here's an example of the kind of equation that I'm talking about. We want to solve the equation 2 to the x equals 3. Before we knew about logarithms, our strategy for equations like this was to write each side with the same base. But if we were able to write the right side in base 2, we would already know the answer to this equation. The answer to this equation is the exponent you have to put on 2 in order to get 3. So trying to write both sides with the same base isn't a very useful strategy here. One way to solve this, I suppose, is to use our translator. Remember that y equals log base a of x if and only if x equals a to the y. So rewriting this in logarithmic form, we get x equals log base 2 of 3. And while I suppose it does isolate the x on the left side, this answer isn't that enlightening. Think about what the original question is asking us. It's asking 2 to what power equals 3. Our answer of log base 2 of 3 means the exponent you have to put on 2 in order to get 3. We've basically just talked in a mathematical circle there. Another way to solve 2 to the x equals 3 is to try to use the properties of logarithms to get that variable out of the exponent. One of the properties of logarithms we discussed recently says log base a of u to the c is equal to c times log base a of u. If you take the logarithm of an exponential expression, you can bring the exponent out of the logarithm. If we apply a logarithm to both sides of this equation, then we can bring this variable out of the exponent and get it down where we can work with it. Now you can apply any logarithmic base that you want, but I'm kind of partial to the natural log. So I'm going to take the natural log of both sides. So the natural log of 2 to the x equals the natural log of 3. And now on the left side, I'm going to apply that property of logarithms. I can bring the exponent down and write this as x times the natural log of 2. The right side would be the natural log of 3. And now I divide both sides by the natural log of 2, and I get x equals the natural log of 3 divided by the natural log of 2. Writing our solution in this format is a little bit nicer, especially if you have an older calculator that won't do logarithmic bases other than base 10 or base e. I can approximate this solution with my calculator by doing the natural log of 3 divided by the natural log of 2. It gives me an answer of about 1.58, and we're claiming that that's about the exponent that you have to put on 2 in order to get 3. That's not an exact answer, I've rounded it, but let's just check. If I take 2 and raise it to the 1.58 power, that answer should be just a little bit smaller than 3, and you can see that it is. If we had added a few more decimal places to our estimate, our result would have been closer to 3. Like if I would have done 2 to the 1.58496, now you can see our answer is really close to 3. You got to remember that the answer we gave here is just a decimal approximation. I want to do more examples like this, but first I want to discuss something. When we rewrote the problem in logarithmic form, we got a solution of x equals log base 2 of 3. And by applying the natural log to both sides, we got a solution of x equals the natural log of 3 divided by the natural log of 2. That indicates that those two expressions must be the same. Log base 2 of 3 is in fact the same as the natural log of 3 divided by the natural log of 2. And this is a specific example of a more general idea that we call the change of base formula. The change of base formula says that we can rewrite log base b of u as the quotient of two logarithms with a different base. So choose any base you want and call it a. Log base b of u can be rewritten as log base a of u, so that's log base a of the original input, divided by log base a of b, that's log base a of the original base. In particular, if you choose base e, then log base b of u is equal to the natural log of u over the natural log of b, and that's what we see in this example. Log base 2 of 3 is the natural log of 3, that's the natural log of the original input, divided by the natural log of 2. That's the natural log of the base. But you can do that for any base you want. So for example, that's also true for the common logarithm. Log base b of u can be written as the common log of u over the common log of b. I like the natural log, so that's what I used here. But going back to the calculator, if we had done the common log of 3 divided by the common log of 2, it's going to give us the exact same result. you can see it's the same decimal. The base that you choose doesn't matter. Based on the calculator that I'm using, the smart bases for me to use would be natural log and common log because I have buttons for those. It will just be convenient. But you can in fact use this for any base. I promised you we're going to get back to solving equations, but since we've already taken the detour to change a base formula, let's just look at a couple of examples of applying it. The first example here says estimate log base 5 of 400. Log base 5 of 400 is the exponent you have to put on 5 in order to get 400. I don't know what that is. I can tell you what it falls between. 5 cubed is 125. 5 to the 4th is 625. So the answer has to be somewhere between 3 and 4. But I can't do much better than that. All I can really tell you is that it falls between 3 and 4. To get a good estimate, I can use the calculator, but a lot of calculators won't do log base 5. So how can I estimate this? Well, I'll use the change of base formula. The change of base formula says pick any logarithmic base you want, apply that to the input, and then divide that by the same logarithmic base applied to the base of the original expression. In particular, this works with natural log. So that's what I would use. I would rewrite log base 5 of 400 as the natural log of 400 divided by the natural log of 5. These two things are equal. And now I can come up with an approximation for that because my calculator has a natural log function. I can just do the natural log of 400 divided by the natural log of 5. I'm expecting this answer to come out somewhere between 3 and 4. And you can see it does. It's around 3.72. So I went from a very broad guess that the answer was somewhere between 3 and 4 to a much more specific answer by converting this to natural log. And there's nothing special about natural log. This also would have worked with common log. If we'd have done the common log of 400 and divided that by the common log of 5, that's also going to give us 3.72-ish. It's the same result because the change of base formula allows you to change to any base. I'm only picking natural log because that's my favorite. You can do this with any logarithmic base. Another thing I should point out, by the way, is that when we divide these logarithms, those ln's do not cancel. You can't cancel the name of a function. Notice that the answer isn't just 400 divided by 5, which would be 80. You can't cancel the ln's. There's an order of operations issue here. You have to plug these numbers into the functions first and then divide. The second example here is a different application of the change of base formula. This asks us to evaluate log base 7 of 8 divided by log base 7 of 2. You cannot cancel the logarithms. The answer isn't 4. We're not dividing 8 by 2. We're dividing log base 7 of 8 by log base 7 of 2. How can we do that? If you read the change of base formula from right to left, it says the quotient of two logarithms can be consolidated into a single logarithm by changing the base into the input of the denominator and making the input to the numerator. So log base 7 of 8 divided by log base 7 of 2 is log base 2 of 8. The input to the denominator is our new base. The input to the numerator is our new input. And log base 2 of 8 is just 3. Is that the only way to do this? No. If you understand the change of base formula, then you know that log base 7 of 8 divided by log base 7 of 2 is going to be the same as log base anything of 8 divided by log base anything of 2. That's what this rule says. So you could just pick a different base, like we could have done the natural log of 8 divided by the natural log of 2. Let's check that in the calculator. Natural log of 8 divided by the natural log of 2 is 3. Common log of 8 divided by the common log of 2 is 3. So instead of rewriting it as a logarithm with base 2, we could have just picked a new logarithmic base for the numerator and denominator and got the answer that way. The change of base formula can be pretty useful in examples like that. But let's get back to solving these equations. This next example is similar to our first example, but I've spiced up the exponent a little bit. It says solve 7 to the 5x minus 1 equals 23. We need to find an exact solution and a 2 decimal place approximation of the solution. Now, one way to approach this problem is to rewrite it in logarithmic form using log base 7. And there's nothing really wrong with that, especially if you have a calculator that can do log base 7. But because a lot of calculators won't do that, what I'm going to do is apply a logarithm to both sides of the equation. And the reason I want to do that is I want to drag this exponent down, and I can use this property of logarithms in order to do that. If you take the logarithm of an exponential expression, you can bring the exponent out front. Bringing the exponent down where I can get to it is a good idea here because that's where the variable is. So I'm going to take the natural log of both sides. The natural log of 7 to the 5x minus 1 is equal to the natural log of 23. Again, the point behind that is now I can bring the exponent down. And what I'm about to write is technically incorrect. When I bring the exponent down like this, I'm not applying the property correctly because the property says that you multiply the exponent by the natural log of the base. In order to show that I'm multiplying the entire exponent by the natural log of the base, I need to trap this in parentheses. Now we need to solve this equation for x, and in this example there are two good ways to do that. One would be to divide by the natural log of 7. There's nothing wrong with that. But the more flexible step that we're going to have to use more often is to distribute, so that's what I'm going to do here. The natural log of 7 times 5x is 5x times the natural log of 7. The natural log of 7 times 1 is the natural log of 7, and that's equal to the natural log of 23. Now I'm solving this for x, so I'm going to add the natural log of 7 to both sides, and I get 5x times the natural log of 7 equals the natural log of 23 plus the natural log of 7, and then I just divide both sides by 5 natural log of 7. And so simplifying, we get x equals the natural log of 23 plus the natural log of 7 divided by 5 times the natural log of 7. Now, this is an acceptable exact solution. You don't need to take it any further than this, but I do want to show you that this can be simplified. Remember that when you add two logarithms, you can multiply the inputs. So this is the natural log of 23 times 7, and in the denominator I can bring that 5 in as an exponent and write this as the natural log of 7 to the 5th power. 23 times 7 is 161, so that's the natural log of 161. In the denominator, 7 to the 5th power is 16,807. So there's a slightly more concise way to write this. But I don't need you to do any of that. That's all optional. What I do want you to do is come up with a 2-decimal approximation of the solution, so I'm going to show you how to type this into the calculator. I'm going to take the natural log of 23 plus the natural log of 7, and I'm going to hit enter on that on its own. Then I'm going to divide that by the quantity 5 times the natural log of 7. And that gives me around 0.52. And there's our decimal approximation. You really need to be careful when you're putting this into the calculator. A common mistake would be to try to type this all in one line using something like this. Natural log of 23 plus the natural log of 7 divided by 5 times the natural log of 7. But there's actually two mistakes here. First off, you're only dividing the natural log of 7 by this expression, and secondly, the calculator is so strict about the order of operations, it's only going to divide by 5. This isn't going to give us the same result. My advice would be to type the numerator first and then divide by the denominator in parentheses. If you insist on doing it all in one line, you would need parentheses around the numerator, natural log of 23 plus the natural log of 7, close the parentheses on the natural log, close the parentheses on the numerator, and then divide by parentheses 5 times the natural log of 7. Close the parentheses, and there's that same result. Because of all of those parentheses that you have to remember, my advice is to just do the numerator first and then divide by the denominator trapped in parentheses. You can see why some people would take the time to simplify though. While this was kind of nasty, it's easier to type into the calculator. The natural log of 161 divided by the natural log of 16,807 is much easier to type and gives us the same result. Now all of the problems we're going to do for the rest of the video are like this. We're just going to ramp up the difficulty by putting variables on both sides. This says solve 4 to the 2x equals 9 to the x minus 3. You can't use a rational number to write 9 in terms of base 4. So we can't use that one-to-one strategy that we used previously. We're going to have to get these exponents down where we can work with them, and I'm going to do that with logarithms, and in particular I'm going to apply the natural log function. So the natural log of 4 to the 2x is equal to the natural log of 9 to the x minus 3. And the reason we do that is that we can apply the property of logarithms that allows us to bring down the exponent. On the left side, the exponent is a single term, so I can just write 2x times the natural log of 4. On the right side, the exponent is a binomial, so when I bring that down, the parentheses are required, x minus 3 times the natural log of 9. The natural log of 9 is just a number, and it distributes like anything else. So on the right side, I'm going to distribute the natural log of 9 to both terms. X times the natural log of 9 minus 3 times the natural log of 9. Because we've got a few more steps here, let me transfer this to another slide and we'll continue. Okay, we're attempting to solve this equation for x. This is a linear equation in terms of x. And our strategy for solving linear equations is to get all copies of the variable to one side. So I'm going to subtract x times the natural log of 9 from both sides. On the left, that gives me 2x natural log of 4 minus x natural log of 9, and that's equal to negative 3 times the natural log of 9. Now I factor out the x. 2 times the natural log of 4 minus the natural log of 9 is left over. That's equal to negative 3 times the natural log of 9. And now I divide both sides by this number. This is just a number. We divide by 2 natural log of 4 minus natural log of 9 on both sides. And so I get x equals negative 3 times the natural log of 9 divided by 2 natural log of 4 minus the natural log of 9. And that is the exact answer. It can be simplified. I could bring this 2 in and write this as the natural log of 16 and then consolidate it into a single logarithm, the natural log of 16/9. But I'm going to approximate this. I'm going to do negative 3 times the natural log of 9. And to stay consistent here, I'm just going to hit enter on that numerator, but if you think you can do this all in one line, please do. I'm going to divide that by parentheses 2 natural log of 4, close the parentheses on the natural log of 4, minus the natural log of 9. And I get negative 11.46 if I round this to 2 decimal places. We could have done this all in one line, negative 3 natural log of 9 divided by parentheses 2 natural log of 4 minus the natural log of 9. Same answer. So the solution to this equation is around negative 11.46. We're rounding to 2 decimal places because that's what it says to do in the instructions. This says 5 to the 3x minus 2 equals 8 to the 2x plus 7. We are again going to find an exact solution and a 2 decimal place approximation of the solution. I'm going to start by taking the natural log of both sides, and again, the point behind that is that I can bring down the exponents when I do that. On the left side, I get the quantity 3x minus 2 times the natural log of 5 when I bring down the exponent. And on the right, I get the quantity 2x plus 7 times the natural log of 8. Now I need to distribute on both sides. So this is 3x times the natural log of 5 minus 2 times the natural log of 5 equals 2x times the natural log of 8 plus 7 times the natural log of 8. Let me put this on another slide. This is a linear equation, so I want all copies of the variable on the same side. So I'm going to subtract 2x times the natural log of 8. Subtract 2x times the natural log of 8. I also want to make sure that any terms that don't have an x in it are on the other side. So this 2 natural log of 5 has got to go to the other side. I'm going to add 2 times the natural log of 5 to both sides. On the left side, we get 3x natural log of 5 minus 2x natural log of 8. And on the right side, we get 7 natural log of 8 plus 2 natural log of 5. Remember, our goal is to solve for x, so I'm going to factor out an x. This is 3 times the natural log of 5 minus 2 times the natural log of 8. And now you just divide by everything that is an x. Divide by 3 natural log of 5 minus 2 natural log of 8. and I get x equals 7 natural log of 8 plus 2 natural log of 5 divided by 3 natural log of 5 minus 2 natural log of 8. And that's a perfectly acceptable exact answer. I do not need you to simplify it any further than that. What we do need to do, however, is come up with a 2 decimal place approximation. I'm going to type the numerator first. 7 natural log of 8, close the parentheses, plus 2 natural log of 5, close the parentheses. Hit enter on that. And then I'm going to divide by the quantity 3 natural log of 5, close the parentheses on the 5, minus 2 natural log of 8. And we get an answer of about 26.55. Now we have our exact solution and our decimal approximation. One more, and I want you to try this one. I want you to pause the video and give this one a shot. Solve 2 to the 5x plus 3 equals 3 to the 2x plus 1. I want you to get an exact solution. You do not need to simplify it. You can leave it as a nasty fraction like we did here. And then I want you to carefully type it into the calculator and get a decimal approximation. Make sure you try this one on your own. You got to make sure you understand how to do this. Okay, so we're going to start by taking the natural log of both sides, and there's nothing special about the natural log except that it's one of the buttons in my calculator. Common log would be a good choice as well. Any logarithmic base would work, but you want to use one that's convenient. Natural log is convenient because it's in our calculator. I'm also lazy and I only have to write 2 letters for that instead of writing log. This allows me to bring the exponents down, so I get 5x plus 3 times the natural log of 2 equals 2x plus 1 times the natural log of 3. Now we distribute and we get 5x times the natural log of 2 plus 3 times the natural log of 2 equals 2x times the natural log of 3 plus the natural log of 3. If you weren't able to get to this point, pause the video now and see if you can solve it from here. We want all of the x's on one side, so we're going to subtract 2x times the natural log of 3. We want to move every term that doesn't have an x in it to the other side, so we're going to subtract 3 times the natural log of 2. That gives me 5x natural log of 2 minus 2x natural log of 3 equals the natural log of 3 minus 3 times the natural log of 2. We can now factor an x out of the left side. 5 times the natural log of 2 minus 2 times the natural log of 3 equals the natural log of 3 minus 3 times the natural log of 2. Now we divide by this entire expression, and we get x equals the natural log of 3 minus 3 times the natural log of 2 over 5 times the natural log of 2 minus 2 times the natural log of 3. I'm going to put this into the calculator as is. I'm first going to find the numerator, the natural log of 3 minus 3 times the natural log of 2. I hit enter on that, and I'm going to divide by the entire denominator. So that's 5 times the natural log of 2, close the parentheses on the 2, minus 2 times the natural log of 3. We get about negative 0.77. Okay, so logarithms have broadened the types of equations that we're able to solve now. We're now able to solve exponential equations where the two bases really don't seem to mesh together. I encourage that you practice more of these, find a textbook and do some practice problems. If you have questions about any examples that I've done or any problems that you try on your own, reach out to me. You can send me an email or we can talk during an office hour.